Hello everyone, my name is Eli Kirk, and this is my project, the rocket payload for the NASA Student Launch Competition. I worked on this project alongside my fellow engineers, my teammates Callista Ray and Ethan Stapleton, alongside the rest of the Central Washington rocketry team, which includes students and professors from physics and then one student from computer science. Now, to reiterate what I've said before, the NASA Student Launch Competition is a nationwide event in which teams from different schools are tasked with designing, constructing, and launching a fully functional subscale rocket to a target altitude, each rocket containing a payload designed to capture a photo upon descent. Now, the requirements for our payload are as follows. It must be delivered to a target altitude of 5,000 feet in the air. The payload must be capable of receiving code via an RF command. It must be able to execute the deployment sequence remotely. The camera must be able to swivel 360 degrees and store the photo on board or send it back to home base remotely. Now, designing something like this was challenging to say the least. Our team ultimately opted for a design focused around the use of a linear actuator. The final design that we have right here obviously uses the linear actuator as a base component, with these three structural plates providing strength and integrity to the payload, along with being the right shape to fit snugly into the body tube. The main idea behind this design is to use the linear actuator to open the rocket, and how this is achieved is by attaching these two plates to the inside of the body tube and this plate to the inside of the nose cone. When the linear actuator extends, it separates the nose cone from the shoulder of the rocket. When this happens, the rotation stop right here is no longer preventing the rotation of the camera mount, and as such, it can rotate freely. With the battery acting as a counterweight, the camera will then rotate upright. It will extend via a spring mechanism and take a photo of its surroundings, thus marking the end of the deployment sequence. Now, my project was not always focused around this final design. In fact, I did most of my analyses on an alternative design of the payload that was originally based around the idea of using a lead screw and a motor system to open the rocket, or open the nose cone rather. I did a lot of column and buckling analysis on this lead screw. I was intending to make this design work. When discussed in a meeting with NASA, they told us that cutting the nose cone open was not a good idea, so we should not do that. And then eventually on top of this, the realization set in for me that I was just creating my own linear actuator, so there was really no point in continuing. When this happened, my alternative design was dropped, and my focus shifted towards finishing the main design with my teammates and beginning construction of the project. Now, construction for this project has been interesting. Prior to deciding on construction methods, this was the payload assembly designed in SolidWorks, and this was used as the base model design for the payload and its components, of course, with everything being continually updated as the project moves on. Our main method of construction for components was 3D printing, though some were machined. We chose the 3D printing because, though our components aren't necessarily the most complex ones, we needed construction that was quickly repeatable, as our designs were changing all the time, and 3D printing afforded us that changeability. The material we chose for these prints was a nylon carbon fiber, and we chose this over PLA or ABS because it is far stronger than either of those and being just as light, meaning that the payload can be lightweight while having its components be strong enough to perform the required functions. Now, the components that we did not 3D print were those made out of clear polycarbonate, being these two plates, their reinforcement pieces, and this rotation stop. These were all made in the machine shop, except for these two plates, which were cut by Peter Zenkat from the physics department using a bandsaw with a rotating base, and I can show that pretty neat little thing. The rotation stop was not that simple. I ran into issues when constructing this because I had no idea how to use the machine shop. I had to get Nate to help me make a specialized tool so I could work the rotation stop in a lathe. When this happened, I was able to cut it, sand it, tap it, etc. Now, the rotation stop, this piece right here, it's a fairly small and simple component, and it took me several hours to make one of them in the machine shop, and I had to make 4. So machining may not have been the most efficient method for manufacturing, and that's why we have so few machined components. Other issues we ran into in construction were assembling the payload with the rocket. That was very challenging. On top of the payload being a struggle to fit inside the rocket, we had to find a way to fasten it to the rocket from the outside. We did this by taping it, as you can see here, drawing lines from basically these points right here along the length of the body tube so we could drill holes that lined up with the screw holes. Other issues we ran into were, okay, so the initial plan was to laser cut the polycarbonate pieces, and we probably would have been able to make more of them if that had worked out. But when we tried laser cutting it, it started just turning into a gross black burnt sludge, and that is just not going to work for our project. Now, before I talk about the testing of this project, it's important that you know the context of the schedule. We were working on an incredibly accelerated deadline for the entirety of this project. Our final launch was on April 15th, and our flight readiness review had to be submitted to NASA by March 6th, meaning that we did not have nearly as much time to test the components as we would have liked, and as such, the payload wasn't able to be extensively tested prior to the launch. The testing that did happen were, of course, the test flights. Then there were general electronic functionality tests, drop tests, ejection tests, etc. Anyway, we gathered a lot of good information from these tests. A great example of this being during one of the test flights when the wires came disconnected from the linear actuator at the end. The payload was able to receive the command, but it wasn't able to deploy because of this. This happening resulted in the creation of the electronics board component, this one right here. And now the wires are secure, the connections are stable, and making this and having that happen in a test flight means that it won't happen again. We were able to prevent that. Smaller tests were, of course, done on payload components just after the fact. For instance, the rotation stop, as I've talked about before, needed to be able to withstand one pound of force during the flight. I found that it was able to confidently deflect only 0.12 inches under 32 pounds of force, meaning that it's way stronger than it ever would need to be. I also tested things like the rotation angle of the camera, finding that it is never, ever going to rotate fully upright. It's just not going to happen. So, fun thing. Anyway, these component tests were successful. The payload was functional. It was well tested. Everything pointed to a likely successful launch. The coding was sound. The payload design was perfect. It was polished. The construction was solid. The vehicle design was ready to go. We were ready, and we launched. And the flight was beautiful. We flew to 4,781 feet in the air, descended in 81 seconds, and landed within 2,500 feet of the launch area, meaning the flight was successful based on the requirements set by us. I keep using that term, the flight was successful, because one thing was not successful, and it was the payload. Now, to be clear, the payload was still functional. It still worked. But what happened was the battery wasn't able to supply enough power to make the linear actuator break the shear pins. Why this happened was, on top of not being fully charged the night prior, the battery was overheated on the launch pad due to the internal temperature of the rocket being 217 degrees Fahrenheit for several hours. So that didn't work, but we went over to investigate the payload after the launch when we went to retrieve the rocket, and after removing that one stubborn shear pin, the payload did deploy. And that moment right there meant everything to me, because it made me realize that despite issues with the battery, the payload, the engineering work that we did was successful, and we had made a functional payload. Now, what does that mean at the end for all of us, right? We put in all this time and effort and then failed in the moment that it mattered most. Well, I don't consider it a failure. I consider it a huge success anyway, because we learned just as much from that failure as we would have if we had succeeded. I have been working on this project in a very disjointed way from the start, from me being sick for the first 2 weeks of senior project, to me working on alternative design out of sync with my teammates, to finding struggles coordinating with the rocket team. It was a convoluted time for me, but I am proud to say that even through all of that, my teammates and I made it work, and we have here a payload that is functional and is able to meet the requirements set by NASA and by us. I know for a fact that I will carry this experience with me into my future in aerospace, and I am incredibly thankful for my teammates, my professors, my friends, everybody who pushed me to keep going and make this project a reality. Thank you.